So here we look at another mode of transport of vorticity, and that is the diffusion of vorticity. And to do that, we are going to look at one particular example, and we will look at what happens to the vorticity of an irrotational vortex. So we are going to assume that we have an initial flow field. So at t equals 0, at the initial times, our flow field will be that of an irrotational vortex. And we're going to locate this irrotational vortex at the origin, so we'll assume that the irrotational vortex is at the location 0, 0, such that the flow field, we've discussed it last time, is going to be at x and at t equals 0. We're going to have no radial velocity component, and in the circumferential direction we have gamma the circulation divided by 2 pi times 1 divided by r. So it's linearly decreasing with the distance to the origin. So as we discussed last time, this flow field corresponds to an initial distribution of vorticity, which is just a delta of vorticity at the origin. So we can write it as our initial distribution of vorticity at x and t equals 0 is a delta function, and how much circulation do we, how much vorticity we have is actually the circulation that will be around the vortex. So that here is our initial vorticity distribution, and now we're going to look at what happens to this vorticity. So we're writing the vorticity equation, and the flow, of course, here is a two-dimensional flow, such that we only have the material derivative of the vorticity vector equal to the diffusion, mu times the Laplacian of the vorticity vector, and there is no source term. And we can write this in polar coordinates, cylindrical coordinates, because the flow is axisymmetric. And so when we write that, we get in 2D an equation for only the vorticity in the z direction, and therefore we get partial omega z partial t plus the u grad u term equals to the diffusion term. Okay, now the flow is axisymmetric, and therefore all derivative with respect to theta are equal to 0. We started from something which is axisymmetric, so it remains in that case axisymmetric. And in addition, the radial velocity here is equal to 0. So that here is also equal to 0. And actually it will remain equal to 0 at a later time, so we can assume that it's going to be equal to 0 here. I'm not going to go into these details. And therefore the equation reduces to partial omega z partial t equals to mu times the Laplacian of omega z, which really just reduces to this term. And so in this case you see that the transport of vorticity is governed by the diffusion equation. So here vorticity is only diffused. And on top of that, you see that one interpretation of the viscosity, and in that case the kinematic viscosity, is that the kinematic viscosity is the diffusivity of vorticity. Note that it has the right units, so the kinematic viscosity has units of a diffusivity, so meters per second. Now remember that this term here initially came from taking the curl of the viscous term of the momentum equation. So if we assume an inviscid flow, we essentially neglect this term here, and so we can think about assuming an inviscid flow as the same as neglecting the diffusion of vorticity. Right, so if you go back to the initial equation here, so when you say the flow is inviscid, you neglect this term, and you say that the diffusion of vorticity is negligible compared to the advection. So it happens over a much longer time scale. Now that gives you another interpretation for the Reynolds number, and the Reynolds number is then the same as the Peclet number that you have seen in advanced heat transfer, but for the diffusion for vorticity. So a high Reynolds number means that the time scale for advection is much shorter than the time scale for diffusion of vorticity. Okay, so this is our equation, right? Our initial condition is that we have a delta function at time equals 0. And so what does the solution look like? This solution you may have seen in advanced heat transfer. It's just what happens to an initial singular distribution. And so if that is here R, initially we have, I don't know how to represent this, but we have a delta. Our distribution is just infinite viscosity at 0, and then we have 0 vorticity elsewhere. And what you have is that this vorticity, which is really concentrated at the origin, is slowly going to diffuse. So it's going to look like this later on, and at a later time like this. And yet at a later time like this. And that here, of course, is as time increases. And analytically, the solution is a Gaussian distribution. So we can write that the distribution of vorticity, omega z at r and t, is equal to gamma divided by 4 pi times t times mu times the exponential of minus r squared divided by 4 t nu. Note that in this solution, of course, if we integrated, what is important here is to see that this corresponds to a conservation equation. So the vorticity, there is no source term, so the vorticity is conserved. So if you were to integrate over at every single time, if you were to integrate all of the vorticity that you have in here, you would get gamma. And same if you integrate at the later time step, and at later times again, you would always obtain the same amount of vorticity in the flow field. So the total amount of vorticity would be the same. And so this is what you get when you integrate this distribution here at any given time t. You would get the same total amount of vorticity. So note here that, again, in this solution, you really have the typical scaling of the vorticity, because you see this exponential here. This term gives you an indication over the distance over which the diffusivity, the vorticity has diffused at a time t. Right? So you see that at a short time t, the vorticity will have diffused over a short time scale. If you go at a later time t, so if I'm looking at this curve here, it will have diffused over a slightly larger length scale. And this length scale is such that, so if I'm calling r the length scale over which vorticity has diffused, so the length scale over which it has diffused after a time t, we see here that r squared scales with, so the extent scales with 4 times t mu. And of course, I'm not such a huge fan of those constant here, so what you find is that the length scale for diffusion scale with the square root of nu times t, where nu is the diffusivity of vorticity. So this is over which length scale has the vorticity diffused over time t. That would be the square root of nu times t. You could revert the question and ask, how long does it take? So what is the time tau for vorticity to diffuse over length r? Well, then the time scale t would be r scale with r squared divided by nu. So you would have tau scales with r squared divided by the diffusivity of vorticity.